So now we are working on homework 2, problem 9, just doing a similar problem to it, and we trained some of the numbers. So how do we approach this problem? Well, in reading it, we see we are asked to test or analyze the physics behind a rock being thrown off of a tower. We're trying to make sure that no one's going to be injured. Right, we want to make sure that rock is going to hit the ground at a reasonable speed. It's not going to be hitting at 200 miles an hour. So the data we're given is the rock needs to land 10 meters from the base of the tower. So let's draw a picture. Let's draw a tower and the ground. So the rock needs to land 10 meters away, and the rock leaves the thrower's hand at an angle of 20 from the horizontal. Now we know he's throwing it down because he throws the rock at the group on the ground. So he's throwing it pretty much directly at these people standing over here, right? So we know it's down and not up, and we know it's relative to the horizontal. So we can draw that 20-degree angle. We don't know the magnitude of the initial velocity, so we're going to have to find that, but we know the direction it points. And the third data point we have is that the rock is going to be in a total time of flight of 2 full seconds. And then it's going to hit the ground so that there is time for a close-up. So we're just taking all these random facts and we're trying to put them into the setting of a physics problem. Now we're trying to figure out what is V final. That is what we need to check, right? Because the set coordinator is concerned the rock's going to hit the ground too fast and it's going to knock out some cement chips and hit the actors, and that would be very bad. So we need to make sure it's going to hit at a reasonable speed. And so we're trying to find V final. Well, we don't really know how to get there yet. And if you don't have any ideas, that's okay. The approach for this problem is best summarized by just trying to plug in random equations until you find an equation which gives you something valuable. So maybe we don't know exactly how to format, like what equation gives us V final. Well, let's see what else we can figure out, right? Let's start at the beginning of the problem. Let's describe the initial motion of the rock. It's thrown down. It's got a V initial x, and it's got a V initial y. V initial y is negative, and V initial x is positive, and this is just V initial. And then we have this 20-degree angle. So we're trying to figure out, what if we could find, V initial x, or maybe we could find V initial y. That seems like it might help us, traverse the problem towards V final. So when we have two-dimensional motion, one of the best things you can do first is just write out the position equation, right? The position equation is x equals x initial plus V initial times time plus 1/2 at squared. The best thing you can always do in these kind of two-dimensional kinematics problems is just write it out and apply that equation to both the x and y components. So let's start in the x direction. Right, we're going to assume the origin is at his hand, that this is 0, 0. So we're not going to have any initial positions, but we do have initial velocities. We have Vix in this direction times time, and there's no acceleration on the x-axis, so that term goes to 0. So this is all we have for x. And in our y-axis, remember again, we have the rock starting at the origin, so there is no initial position. The initial velocity is VIY times time. And we do have an acceleration in the y-axis, right? We have plus 1/2 times negative 9.8, because that rock is in free fall. So it only experiences gravity. So we now have two equations to describe the position and motion of the rock. Well, let's go back to our original problem. We had 20 degrees, time of 2 seconds, and an x of 10 meters. That was what was given to us. And if we look at our first equation here, we see that x equals v initial in the x direction times time. Well, we have at t final, at 2 seconds later, the rock is 10 meters away. The rock is 10 meters away. We don't know what v initial is, but we know that time at that t final is 2. So we can use an equation that we found from the initial point, and then we plug in our conditions from the final point, and now we've actually figured out that our initial x component was just 5 meters per second, right? So the best thing you can do when you're approaching a problem and you don't know where to start is draw a picture and represent the position and the x and y coordinates and the position equation, right? Just apply the position equation, right? Maybe you don't even know what you're doing. Maybe it's not even the right context to use the position equation, but it's always helpful and it's going to get you out of a lot of binds when you're just staring at a problem blankly and you're not sure where to start. So now that we have Vix, let's go back and look at our vectors that represent the initial velocity. We know now that Vix is 5. We have our Viy, which we don't know yet. We have Vi, another unknown. We have 20 degrees. And if you remember, we have 2 data points. We can actually find Viy here using tangent theta equals opposite over adjacent from SOHCAHTOA. And so we see that tangent 20 equals, well, our opposite is Viy divided by our adjacent of 5. And so we found that our V initial in the y direction is 5 times tangent 20. And we'll put that in the calculator and we will get 1.82. And yeah, we're rounding to 2 decimal points, and so it's going to be a little bit inaccurate. And if possible, it's always better to use that 10-digit answer your calculator outputs and to keep using that through all your work. But it can be a little complicated to try and track all those numbers. So now that we have this, and it's in units of meters per second, we have our V initial in the x and y directions. Well, what if we go back and we look at our y-axis, right? It's kind of the only equation we haven't used yet. So let's see. Why don't we try and think about our deliverable? Our deliverable is V final. Well, the only equation we have really that describes V final is V final equals V initial plus acceleration times time. Well, we can figure out that our V final in the x-axis is V initial in the x-axis, which is 5. Well, x-axis experiences no acceleration, so our final x component is still just 5. And now we can go on to the final y velocity. We go back to our initial y. The initial in the y direction is 1.82 plus our acceleration of negative 9.8 times time. Well, the object's in flight for 2 seconds. Now, where did we go wrong? What we're going to find is that this is incorrect. The reason why is that our initial y component needs to be negative, right? We see that it starts pointing down and it's going to keep gaining speed. If you wanted, you could indicate that this is the positive y direction. You could turn that positive and you could turn your 9.8 to be positive. But that's not going to really help us in this problem. And so it's really important that we keep track of the initial velocity being negative. We want that negative 1.82 minus 9.8 times 2. That's going to give us our V final y. So we find it to be 21.4 meters per second. And so we have the x and y components. The last thing we have to do is use the So now that we have our final velocity in the x and y direction, well, we need to find the magnitude. If we remember, we have an x component of 5, a y component, make sure that's negative, negative 21.4. Well, that creates a vector here. We need to know this v final. We got to figure what that is. Well, you can say v final is equal to the square root of 5 squared plus 21.4 squared. And we can put that negative in there, but it's not going to make a difference since that term is squared. That negative is going to go away. And so we find v final. We find v final to be 21.99 meters per second. And that is our final v final. That's our final answer, right? This is how fast it's going. But here in America, we don't know. Nobody really has a concept of what a meter is. And so we don't really know how fast a meter per second is. And it sounds pretty fast because a meter is a pretty long distance and a second goes by really quick. Going 22 meters per second is a pretty fast speed for a rock. But if you really want to have a good understanding, you have to convert from meters per second to miles per hour. And so if you convert 21.99 meters per second, and the way I like to do this is just by Googling a meters per second to miles per hour converter, rather than going through the dimensional analysis, because that could take a long time. Well, we're going to find this to be 50 miles per hour. Now that's pretty quick, and I would not want to be in front of a rock traveling at 50 miles per hour. So I would say that this is too dangerous. But in the context of this problem, we're really just trying to find what it is, and we can make an assessment, but we are going to leave it up to that set coordinator to figure out if this is too dangerous. All right, so in this problem, we just found the final velocity given a very minimal set of data describing the initial condition of how far the rock is going to go, the angle it's thrown at, and how long it's in the air. We found v final to make sure that we aren't going to throw a rock too fast at the actor standing below.